We now reach our final section of chapter 6. So chapter 6 about normal probability distributions. Began with the standard normal distribution represented by that bell-shaped curve. And then in 6.2, we looked at real applications of a normal standard distribution. And what we're able to do with that is, if you know that a population has a normal bell-shaped distribution, and you know the standard deviation and the mean value from the population, then given an individual's value from the population, you can use their comparison to the mean with the standard deviation to see how extreme that value is. Are they in the top 10%? Are they in the middle 30%? You can even see what portion of the population is at any point in the range values. So that was very valuable and gives us very quickly a way to see how important having that data about a population is for working with individual values. That was in 6.2. So then last time on 6.3, last week, we looked at sampling distributions with the idea that you take samples of size n and then you look at the means of the samples or the proportions of the samples, and you imagine all possible different sample values forming a distribution and whether that's a normal distribution or not. And then in 6.4, we have the central limit theorem that basically says, well, when you do that, you can do the same thing that we did for individuals in the population, seeing how extreme that value is, but with sampling distributions. And again, I will have posted the video for the 6.4 introduction by tonight. So there are 2 more sections in the chapter, but as I mentioned at the beginning, we're not going to cover 6.6. It's an extra section that we are opting out of. So all of our work finishes in today's section, which is 6.5, Assessing Normality. So part of what happened earlier is, since we're relying on normal distributions, it then becomes important to try to be able to determine or assess whether a population's values are normally distributed or not. And we're going to look at a couple of different ways to try to assess whether a population's values that you're collecting are normally distributed or not. We're assessing normality in 6.5. That's today's goal. And this will involve a couple of graphical methods specifically. And we've done this a little bit in earlier chapters, but we're going to do it more rigorously now. So key concept. In this section, we present criteria for determining whether the requirement of a normal distribution is satisfied. So they're saying it might be a requirement because in the previous section in 6.4, this thing called the central limit theorem, one of the requirements that can be met to use the central limit theorem is that the population that you're drawing your data from, the data is normally distributed across the population. And so that's why that's a requirement that you might want to see if it's satisfied or not. And we're going to look in this section on how to do that. The criteria involve: 1, visual inspection of a histogram to see if it is roughly bell-shaped. 2, identifying any outliers. And 3, constructing a normal quantile plot. So we've actually done all of these things before, but the normal quantile plot didn't come up much in the past. But we're going to revisit all of these issues and put them together as a package of criteria that will allow us to try to determine or assess whether data drawn from a population has a normal distribution in the population. So the first one is a normal quantile plot. So with a normal quantile plot, they're going to define it very carefully. They're going to give you formulas for how you might create one of these graphs by hand. But I'm going to kind of skip through that because we're going to rely on StatCrunch to simply make normal quantile plots for us. And we want to work much more on looking at a normal quantile plot and interpreting what we see. And the slides give us several examples to help develop that intuition. We're going to want to get to a point where we can apply some judgment when looking at a graph to assess whether we believe the normal quantile plot, or the QQ plot is how it's referred to in StatCrunch. If the QQ plot is showing that the population's distribution is a normal distribution. And so I'm going to want to spend a little bit more of our time today focusing on looking at graphs and judging those graphs to determine normality, rather than the details of how the graphs were constructed. So it says it defines a normal quantile plot as a graph of points x, y, where each x value is from the original data set, and each y value is the corresponding z-score that is expected from the standard normal distribution. So they're basically going to give z-scores to every data value and then plot points with the value of the data and the z-score of that value if you had a standard normal distribution. And the idea is, on that graph, if you had a standard normal distribution, the graph would be very well organized, because z-scores do organize well if you have a normal distribution. But if the original data set is not normally distributed, then you will see that on the graph, as we will see in some examples. So here is a procedure, 2 slides to describe a procedure for determining whether it is reasonable to assume that the sample data are from a population having a normal distribution of that data. As we just discussed, there's 3 criteria. 1, histogram. Construct a histogram, which we have done in chapter 2. If the histogram departs dramatically from a bell shape, conclude that the data do not have a normal distribution. So you're looking for that lump in the middle somewhere. It doesn't have to be perfectly in the middle of your histogram, but it should be somewhere centrally located with some symmetry, as opposed to heavily skewed or not bell-shaped. Outliers. Identify outliers. If there is more than 1 outlier present, conclude that the data might not have a normal distribution. You can do that mathematically by doing the definition of an outlier as being more than a 1.5 standard deviations above the interquartile range or below. You may recall that from earlier. However, we're probably more going to be doing that graphically. We're not looking for you to do mathematical calculations. If you look at a graph of the histogram, or even of a QQ or normal quantile plot, you can see if there's a couple of values that seem way as outliers from the rest of the data. Usually graphically is sufficient. And then third is to look at a normal quantile plot. And if the histogram is basically symmetric and the number of outliers is low, then you can use technology to generate a normal quantile plot. Now, they're giving that as a third option here because this criteria was developed in a time where technology wasn't as easily accessible and prevalent as it is now. But of course, truth be told, you could also just grab a normal quantile plot right away, because for us, it'll be extremely easy to do. So let's see these in action. Well, let's finish their summation of the procedure. Applying the following criterion to determine whether the distribution is normal. They can be used loosely for small samples, but they should be used more strictly for large samples. Normal distribution. The population distribution is normal if the pattern of the points is reasonably close to a straight line, and the points do not show some systematic pattern that is not a straight line. This is referring to the normal quantile plot. So when you make this graph of the data values with their z-scores, if the data comes from a normally distributed set, then you should see these points line up in a straight line. And if they don't, like and then some sort of a cloud, or if they seem to kind of have a curve that's a systematic pattern that's not a line, then that suggests that perhaps the population it comes from is not normal. So not a normal distribution. The population distribution is not normal if either or both of these 2 conditions applies. The points do not lie reasonably close to a straight line. Again, this is on a normal quantile plot. The points show some systematic pattern that is not a straight line. So we need to look at graphs to develop this judgment sense, this sense of looking at the graph to make these conclusions. So let's proceed. So here's an example of a histogram on the left and a normal quantile plot on the right. And they're saying, here's an example to help see what a normal distribution might look like. The first case shows a histogram of IQ scores that is close to being bell-shaped, meaning the histogram itself looks like a bell-shaped curve. The corresponding normal quantile plot shows points that are reasonably close to a straight line. And the points do not show any other systematic pattern that is not a straight line. It is safe to assume that these IQ scores are from a population that has a normal distribution. Questions, comments, discussions about this example of the graphs showing it's a normal distribution?
So because has such a good line of best fit, that makes it normal?
Well, it's not, keep in mind, the graph is not of the data themselves. The graph is a special kind of graph of the values of the data together with their z-scores. And the reason I want to say that is later we will look at this thing called a line of best fit, since you used that phrase. But the line of best fit will be a line that fits the data values themselves, not their normal quantile plot points. So in this case, for checking normality, because the normal quantile plots seem to match their line of best fit, then you draw the conclusion that the population is normal.
Makes sense. Thank you, sir.
And of course, to see, well, when does it not look like a line, the next examples will show counter examples to these. But yeah, we're basically looking at how nicely that fits on the line in that example shown here. Okay, so let's see when it's not normally distributed. So here is an example of uniform distribution. We've discussed a uniform distribution before, but I do want to assure you, you're not expected to look at a normal quantile plot and conclude from that that you have a uniform distribution, only that it is not normally distributed. Now, from a histogram, we can see a uniform distribution pretty nice and clearly. All right, so in this case, it says the second case shows a histogram of data having a uniform or flat distribution. The corresponding normal quantile plot suggests the points are not normally distributed. They have a very nice pattern to them, and the pattern doesn't deviate very far from the line in general. And it points that out. It says, although the pattern of points is reasonably close to a straight line pattern, there's another systematic pattern that is not a straight line pattern. The pattern that the points are adhering to are curved, and you can basically see that in the first period, they're all below the line of best fit. And then for the next period, all at the same time, they're all above, and then they fall all below. And you can see this kind of nice, slightly curved pattern. So even though they're not very far from the line, they do show a systematic pattern that itself would not be a straight line. And we conclude that this sample, therefore, are values from a population not having a normal distribution. And we can see that actually it's not normal at all. It's a uniform distribution. But this is what this uniform distribution looks like when you put it on a normal quantile plot. Okay, so one of the things I want to point out is what we're trying to accomplish as we look at these examples is that you want to be put in a position where you can recognize the difference between this normal quantile plot and that normal quantile plot, and why they would say, yes, this looks like this could be from a normal distribution, whereas this is an indicator that it is not from a normal distribution. So we're trying to look at these examples to help us develop our own sense of judgment so that in problems, they can give us data. We can look at these graphs and draw conclusions correctly. You're trying to develop that skill as we go through these examples. Next. So here's a skewed example. The third case shows a histogram of the amounts of rainfall in inches in Boston for every Monday during 1 year. Looks like there's a rainy season and not so much the rest of the time. The shape of the histogram is skewed to the right fairly aggressively, not bell-shaped. The corresponding normal quantile plot shows the points that are not at all close to a straight line pattern. These rainfall amounts are not from a population having a distribution that is normal. This is not normal population distribution. So one of the things to draw from this is that there are plenty of examples of things measured in the real world and data sets that are not normally distributed, that do not have a normal distribution. Normal distributions are very common, and when we have that, then we can do a lot of good statistical work with that. But it is quite possible that populations of data sets do not have a normal distribution. These are actual data sets that are being used in all of these examples. All right, so tools for determining normality. So the histogram and the outliers, as they mentioned before, if the requirement of a normal distribution is not too strict, meaning sample sizes aren't too big, simply look at a histogram to find the number of outliers and find the number of outliers. If the histogram is roughly bell-shaped and the number of outliers is 0 or 1, treat the population as if it has a normal distribution. Or alternatively, a tool is the normal quantile plot. Normal quantile plots can be difficult to construct on your own. Happily, we won't be doing that. But they can be generated with a TI-8384 Plus calculator or suitable software, such as, and in our case, StatCrunch is the last one listed. So we will typically, because they're so easy for us to use, you can, for any of the problems that we do, look at the histogram and the normal quantile plot. In advanced methods, in addition to the procedures discussed in the section, there are other more advanced procedures for assessing normality, such as the chi-squared goodness of fit test, et cetera, et cetera. Okay, thanks. So now they're talking about the manual construction of a normal quantile plot. And as I was mentioning, I'm going to kind of skip over these, because there's no point in this class where you will be asked to construct a normal quantile plot manually. So they have a special kind of Ryan Joyner test that they kind of thrown at the end. I don't recall seeing this on any of your homework problems, so it may be a non-issue. But it says it's one of several formal tests of normality. These are typically used for larger data sets with larger samples. And it says one of several, each having its own advantages and disadvantages. StatDisk also has a feature of normality assessment that displays a histogram, a normal quantile plot. We're not going to use StatDisk. Old faithful eruption times. We can use the normality assessment features of StatDisks with all 250 eruption times listed in the old faithful data set to get the accompanying display. So notice that in this technology use that they're illustrating, the key features are some stuff that we haven't talked about yet, which we'll talk about later, like test statistic, critical value. We will revisit the idea of normality, I think in chapter 11, in the last chapter that we covered. But for the purposes of what we're looking at now, it also in this little StatDisk package comes up with a normal quantile plot and the histogram. And we looked at the old faithful eruptions with the histogram part previously when we saw these sort of two different subsets illustrated by the histogram, each individually looking like they have their own mini little normal distribution, but taken as an overall data set on the whole, that means that it's not a normal distribution. And the normal quantile plot illustrates that pretty clearly as well. Okay. So then they draw some conclusions or talk about this example. Let's display the three criteria. For the histogram, we can see the histogram is skewed to the left and is far from being bell-shaped. Outliers, the display shows there are 20 possible outliers. If you look at the kind of graph here more closely, in the normal quantile plot, you can sort of see little clumps of outliers there. And the normal quantile plot, whoa, the points in the normal quantile plot are very far from a straight line pattern. We conclude the 250 eruption times do not appear to be from a population with a normal distribution. And then they talk about some other things that are sometimes used when looking at data, which we will not be doing in any of our problems. So I'm not going to worry about that last slide. And that's all they have for us. So the main things we want to get out of this introduction, and then we have time, we're going to do several problems from the homework. I think I already saw 3 I wanted to take a look at, is these graphs, these first 3 graphs, the idea of what normal graphs look like, and what graphs look like when they suggest that the population's data set is not normally distributed, either from a systematic pattern that deviates from a line or just overall pattern deviates from the line on the normal quantile plot, as well as the histograms. All right, so hopping over to some homework. All right, I think I wanted to start with maybe 20, 21, 22. Those all looked good. All right, so I'm pulling up number 20 out of 29. And as you can see from the label here, this is from our final section of the chapter that we're going to look at, 6.5. Let's do similar question, get some fresh data. So it says sample data for the arrival delay times in minutes of airline flights is given below. Determine whether they appear to be from a population with a normal distribution. Assume that this requirement is loose because the sample size isn't very large, in the sense that the population distribution need not be exactly normal, but it must be a distribution that is roughly bell-shaped. So if we click on the data set here, we can take a look at what the data looks like a little bit. So they don't have a ton of data values here. Looks like something like 40 or so. And some of them are negative because maybe a plane arrives early, and the positive numbers, I guess, would be minutes that it arrived late. And a 0 would be right on time, but I don't see, oh, there's a 0. First one's 0. So there's a flight that was right on time. So that's what the data set looks like. And we're supposed to assess normality. Now, if we look at some of the options, if we're picking one of these, it says, is the requirement of a normal distribution satisfied? It has discussions about the histogram and the points lie reasonably close to a straight line on a quantile plot, normal quantile plot. So they basically want us to look at these 2 things and then pick the correct conclusion with the justifications given. And 2 of them are yes and 2 of them are no with the variety of justifications. Okay, so how would I do this? I would transfer the data into StatCrunch. And once I've got that over there, I don't need to look at it over here anymore. And so both a histogram and a normal quantile plot are types of graphs. So for these things, we'll be working off of our graph tab. And histogram is here, which we can remember from chapter 2. And normal quantile plot is the QQ plot. So let's say I look at the histogram first. I go histogram. And I basically select the column and leave all the defaults alone, and I hit compute. So there's our first graph. So we could right there be sort of saying, do we believe already that this is normally distributed or not? What do you guys think?
No.
And how could we describe this graph?
Skewed right?
Yeah, that's exactly right. Nicely done. So that's a pretty quick way for us to say that. And I do have some chats coming in real quick. And yes, also Amelia said right skewed, exactly. All right, but let's go ahead and follow up with the QQ plot. So I go QQ plot for normal quantile plot. Again, I pick the column and I can leave the defaults because I'm just looking to see how close it forms to a line. Do you think that the normal quantile plot, and you can see here, even though it said QQ plot on the list, here it does say normal quantile. Do you think that that would lead you to the same assessment of no normality?
Yeah.
And why is that? There were two things, either systematic deviation from a line or just generally not close to a line. Well, we have a couple things going on here, but definitely there's a systematic deviation because you can see there's this curve on the whole. So some sort of like parabola or something would fit the data much better than a straight line. Also, you can see there's some outliers, it looks like up here, which were also kind of indicated a little bit by the histogram. And that's why I said a lot of times you can kind of look at potential outliers graphically much more easily than mathematically with a formula. All right, so we now need to pick the correct conclusion. It's definitely one of the no's. So if I look at the first one, it says no, because the histogram of data is bell-shaped. There are less than 2 outliers, and the points in the normal quantile plot lie reasonably close to a straight line. So on number C here, it says no, but then all the reasons for saying no are reasons why you would say yes. So I'm thinking it must be D. But let's read it through. No, because the histogram of the data is not bell-shaped. It's not, it's skewed. It's not symmetric. There is more than 1 outlier. These don't have to all be requirements, but it looks like there are. And the points in the normal quantile plot do not lie reasonably close to a straight line. You don't need to have all of these conditions met. Any one of these conditions could indicate it's not a not from a normally distributed set. Okay, let's move on to the next question. Okay, so now it says refer to the data set below. And in this case, we have body mass index of men. An example, again, it's not a very large sample. In this case, they just show it to you there. And determine whether the requirement of a normally distributed distribution is satisfied. Assume that the requirement is loose, so it doesn't have to be exact. You're just looking for basic normality. And then you're supposed to draw a conclusion with a rationale. So in this case, it doesn't even tell us what to use. Now, if we look at the answers, it does say normal quantile plot. So everything they're talking about is just referring to a normal quantile plot. That means we can look at a histogram, but it's not part of the rationale that they're using for the answer of yes or no. So I would still, either way, open the data up in StatCrunch. Go to the graph tab, and let's just say we do what they want, go right to the QQ plot, select compute. Now, let's say you're unsure. You could say, well, it looks like it deviates because, again, this is a judgment call, and maybe some cases, whoops, are easier to judge and others are not. And so it's not a perfect science. It does say it's loose, but are you willing to form an opinion?
Yes. So I would say like it's letter D, like the answer is letter D because there are more than 1 outlier.
So where do you think you see more than 1 outlier? On the right or the left or what?
At the right, at the end of the graph.
These here are outliers?
Yes.
Okay, so I think I would probably not agree with that, even though I understand exactly what you're saying, but these don't feel or look to be very far away from the rest of the data. There's a little gap there, but remember, an outlier usually needs to be more extreme, and the gap, I think, would normally be larger. But normally, notice how I'm comparing this to the normal situation, which is a judgment call. Does that make sense? I don't actually see these as being outliers in the set. Because remember, with a normal distribution, you're going to have more data in the middle, and data is going to be more scarce on the ends normally with a normal distribution in a bell-shaped curve. So the fact that they're a little spread apart from each other and from the lump of stuff in the middle, that's happening kind of symmetrically on both sides. So I wouldn't see that the outlier aspect being a sense of lack of normality in this case. Does that make sense?
Yes, yeah.
Let's see what the histogram looks like, even though it doesn't ask for that. But there, you just a couple clicks and you've got the graph. So it's kind of like we want to take advantage of the ease of use here. So my honest judgment is that this is pretty normal. We have this one little sort of deficit here, but literally if this one class was up there, it would be almost perfectly normal. And it does say that this is in a loose sense. So I think they would want to show, I don't see a skewing. It's fairly symmetric. There's just this one gapped area. So honestly, I would choose A. Well, let's see if I'm wrong. That's what they want. So that's why I was saying that it is definitely the case that there might be some of these where you're tempted one way or the other, or you're just not sure, and that's normal. You are part of a normal population. And that's why we want to go through some of these problems and look at examples to get a sense of how far things have to deviate from the line and in what way for us to feel more comfortable to say, no, that's not a normal population. Questions, comments, discussions about this example? All right, let's keep going. Yeah, we got still time. Let's do another one. Doing all your homework for you. All right, so in this case, there's a little bit more to look at. Let me go similar question here. So it says, use a calculator or computer software to generate a normal quantile plot for the data in the accompanying table. Then determine whether the data come from a normally distributed population. So we have to pick from, looks like we have 3 choices here. And so I would point out that the choices are fairly similar, meaning that they're not, obviously we would be able to possibly draw different conclusions, but that they don't look drastically different from each other. We would need to have something comfortable to look at to draw conclusions safely. And so we're going to need to make a quantile plot, a QQ plot, and compare it to these so we can choose correctly. Now, in the slides, whoops, I'm going to just go ahead and move these over to StatCrunch. In the slide introduction that I did, they defined the normal quantile plot by saying that the order point values are generated where the X value is one of the data values here, which are space flight durations. And so the space flight durations are the X values here from 0 to 500. And then remember, the Y value are Z-scores, and Z-scores, as we've been learning, are usually numbers in the -2 to +2 range. And you can see those along the Y-axis. Right, now I'm pointing that out because the way they defined it in the book and the way they're showing in these graphs that you're picking from here, the axes are reversed from the default in StatCrunch. So now that I got this data here, if I go to graph and go to QQ plot, which I did before, I could just pick the column and make a graph quickly. There you go. But notice on the graph from the StatCrunch, the values on the Y-axis are the ones in the hundreds, which they have on the X-axis. And the -2 to 2 Z-score values they have on the X-axis. And in the book, they have those on the Y-axis. And so if you were to make a graph quickly the way I just did using the defaults, you'd probably have to think about switching the axes in your mind when you're comparing to one of these graphs. Now, switching the axis has nothing to do with whether the points lie reasonably close to a line. So you don't need to change from the default to make that conclusion. But if you're comparing to graphs that they've made, you might want to switch the axes, which you can also do. So let me show you how to do that. So if you don't want to have to think about flipping the graph and you are comparing to previously made graphs in on the book using StatCrunch, then what you can do is if you click here on other options, it says normal quantiles, those are the z-scores, on the y-axis. So in what we were just looking at, StatCrunch had put the z-scores on the x-axis. Clicking this moves them to the y-axis and moves the data values to the x-axis, and that's how the book does it. So if I click on that little box, then my graph will be also oriented the same way as their graphs. So if I've done that, and I could try to make the shape of the graph match theirs a little better, maybe like that or something. Also, they're going -2 to 2, and here they go 3 to 3. And these guys stop at 400, so this is a little over 400. These guys go to 500 and never reach that ending value. So do you think looking at this, you could pick the correct graph from A, B, and C?
Yes, I think it's number A.
I agree. I think you're right.
I mean, letter A. Yeah.
Yeah. Now, one of the things you could see also if they are kind of close or small is that you can make the graphs bigger over here. And then you can actually compare individual values, like imagining what these, and notice like these have a bunch of values all with the 0x value. And these have like a bunch of values all, and these are all like lined up with the same values. And this clearly does not have that shape. Similarly on this one, so you can make these bigger if you want to look with more detail. This has values that start below the line of best fit, where these values start above the line of best fit. This also has a very clear systematic pattern of deviation, whereas this does not have that clear systematic pattern of deviation. So you can look more closely, but without even having done that, yes, A is the correct choice here. Were there any questions about how I created the graph in StatCrunch to compare to the ones offered in my stat lab? Okay, so then let's look at their conclusion. What do we think? Is this from a normal distribution or not?
I would say normal.
Certainly they look pretty darn close to the line, right? And they do have this example here that's not the correct one, where you have that same sort of closeness to the line, but you have a more clear pattern away from the line systematically. And so I think this is supposed to be, in comparison to that, an example of how you don't have a systematic deviation from the line. So which choice is that? Well, the distribution is normal, is A or B. And A says normal because they show a systematic pattern that's not a straight line. So that's a reason for it to not be normal. So that means it must be B.